Hi everyone, today I'm talking to Filip Rozpędek regarding quantum repeaters based on concatenated bosonic and discrete variable quantum codes. Filip was kind enough to prepare a presentation for the discussion today, so we're going to be stepping through that as we talk about the quantum repeaters that he's presenting. I hope you enjoyed.
Right, so basically our work is on, there are so many of these strategies to build to how we envision we can try to build the quantum internet. And the reason why we want to build the quantum internet is that we hope to have all these interesting applications. Like I think that the most famous one for in the communication setting is quantum cryptography. And I think the one for which we have let's say mathematically worked out very well is quantum key distribution, and that's also the one for which there is also like it's already commercially available technology on short distances. This is quantum key distribution. But then there is also like so for quantum key distribution, the requirements for short distances are actually hardware wise very moderate, and that's why this is something that we can already do. But then if we start to having access to more advanced devices like these nodes will have access to quantum memories, then we would also be able to do more advanced things like these things related to metrology, like say sensing. Then there are some applications also in cryptography that extend between beyond two-party protocols to multi-party. And then like kind of the things that we think would be one of the most advanced is once we have quantum computers, we can have the internet that connects them. So we could have some networked quantum computing setting.
Is there, if I can just jump in there, is there some idea for how to connect, like let's say we have a quantum internet and then we're using quantum computers on this, let's say web. Is the idea then that you would transport the quantum states directly between the quantum computers? And if so, are there any like concrete benefits that we can see already that would sort of come from that? Or what's the idea for trying to construct it in, like, are there any utilities except for the, let's say, enhanced security that you might get from a quantum internet?
Right. So I think here it very much depends what setting we are looking at, right? So we can look at a large-scale quantum internet where you really have multiple computers that are very far away from each other, and this is really like you're connecting distant locations, and then you are performing some distributed computation where the devices are space-wise by the nature of the task you are performing, that there is one person on one side that wants to do something on the other side. Maybe so in some, let's say, simpler setting where before even going to this fully blown quantum computers where everyone has a quantum computer, you can have things like blind quantum computing where there is a server that provides some like blind delegated quantum computing, where there's the server that provides some quantum computing capability. I don't have a quantum computing capability and I would like to use that server to compute something for me, but I would also like to do it in a way that the server doesn't know what I'm computing, and so then I'm using this quantum internet to exchange my data with this quantum computer. But then there are also scenarios when you can think of a local quantum network, like between it's not something that is distributed across long distances, but maybe between, you have network between in a lab or between two labs, between multiple chips, simply because you're putting too many qubits on a single chip or in a single location might be very hard, and then kind of controlling all of them because you need to put all these wires and these connections that enable to implement gates at some point might be tricky. So it might be simpler to maybe have things a little bit space-wise separated. So you might think also about connecting, dilution refrigerators that are in neighboring room or even in the same room, but that's also, you would argue, is some sort of small quantum network.
Right.
So yes, I would say that all those different scenarios, and I think ultimately my perspective is that a lot of things we are still at a very kind of early stage where a lot of things might transpire later, simply because we are still actually thinking of new applications, like writing new protocols for quantum computing. And then of course for every new protocol, it's kind of the question what kind of resources one would need, and that determines then what kind of hardware is needed, and that determines what kind of connections are needed. So does that answer the question?
Yes, that answers it. Thanks.
Okay. Right. So we have. So I would say that we have a lot of these applications, and then the ones that the ones related to cryptography are kind of the simplest ones because they often don't even require quantum memories. But the actual issue is that if we want to build these large-scale quantum networks, we would need to have also not only this ability of the end nodes to connect to the internet, but we would need to have some kind of quantum switches, and then this quantum repeaters that we will talk about here. And so this slide is actually from the Center for Quantum Networks, of which I'm part of, where we are actually envisioning to build such a prototype of such a quantum internet. And so here in this talk, I will focus on these quantum repeaters. And so here, using the slides from my PhD defense, well, so basically the main problem with this quantum communication, and the reason why quantum key distribution exists on short distances so far commercially, is because the no cloning theorem tells us that we cannot just simply amplify the quantum states of photons in the fiber in the way that we amplify our classical communication. And in the fiber, because of the absorption and scattering properties of the fiber, the rate decays exponentially. So if we want to distribute these quantum correlations, entanglement over long distances over a direct transmission channel, that would take a lot of time. So the idea of a quantum repeater is some kind of device that you put in the middle that is enable you to split this end-to-end communication into some kind of shorter distances. And then this quantum repeater is supposed to enable you to independently maybe generate the entanglement between, say, Alice and the repeater and Bob. And then the quantum repeater would do some kind of operation that connects these this short distance entangled links into long distance entanglement, and that serves as a effectively end-to-end entanglement that is now achieved when we can overcome this exponential resources. So other way of seeing that is that you basically generate these short distance links, and then you use one link as a resource for teleportation of the other qubit that is in the middle, such that you establish the end-to-end link. So this is how the original quantum repeater proposals were working. And so the idea was that you would generate a lot of these short distance elementary links, and then you would connect them using these Bell measurements, which are these 2 qubits measurements that project the state onto a maximally entangled state. Is basically this Bell measurement corresponds to an operation of a control NOT gate and 2 single qubit measurements, and then at the end you would be able to establish an end-to-end link.
Can we maybe go into some more conceptuals on that particular point? Like when we have the Bell measurement and we're splitting these, so we have this connection channel and we're splitting it up into small segments, and then we're using Bell measurement as a way to transfer then I guess the entanglement between the two particles, or the entanglement from the first segment, let's say, to the other, right? How do you have some conceptual understanding for how that works? Like how you're able to take this entanglement and transfer it with the help of a Bell measurement? The context that I'm familiar with when it comes to Bell measurements is essentially to prove the quantumness, let's say, of a system, but I take it that you can also use it then for this kind of practical application where you want to transfer a state from one location to another.
Right. So Bell measurement is basically effectively, you can say it's a projector on a maximally entangled state, and that you can effectively think as an operation that enables you to perform teleportation. So maybe let's go here. That would be easier. Let me put the laser. Okay. Oh, I see. Okay. So an important point. So Bell measurement is not the same as the Bell test. These are very different things. So maybe you are referring to a Bell test.
Okay. Then there's probably a confusion there on my part. Would you mind explaining what the difference is then? Or like how, well, okay, I guess there's a big difference in that case. But would you mind giving, let's say then a high-level dummy explanation for a Bell measurement?
Yes. So Bell measurement is basically a 2-qubit measurement that projects the 2 qubits into an entangled state. So basically, instead of measuring a single qubit individually, for example, you perform a measurement that, let's say, the entangled pair can be a superposition of 0, 0 and 1, 1. But that's actually what you're trying to prove in a Bell test, where basically you don't really know whether you're, like fundamentally, your state is simultaneously in the 0, 0 plus 1 and 1, 1. And there is no kind of classical description of that. That I guess was something that you referred to in the Bell test. There is no classical description that this superposition of 0, 0 and 1, 1 does not arise from our lack of knowledge on the system, but arises from the fact that quantum mechanics does not obey this local realism. And so now the idea is that you can actually perform a measurement on two particles that actually projects them on in such a state. So let's say you have two particles that don't have these quantum correlations. And if the two particles are in the same location, you can perform a measurement. So it's operation on these two qubits such that they become entangled. And generally what is regarded is that generating entanglement locally is easy. The difficult part is generating the entanglement remotely over long distances. So this measurement that you do here, this operation actually is an operation that performs such a measurement. So if you have these two qubits A and B, and then maybe they are not entangled, if you do this measurement effectively. Or maybe let's think differently. Let's say these qubits A and B are already in some entangled state. Then if you do this control NOT gate and then you make the single qubit measurements, then even though you are doing single qubit measurements, because we have acted with this two qubit gate, we are able to read what kind of quantum correlations there were between these qubits A and B. So somehow you can argue that this measurement is a reverse of a local preparation of the entangled state. So a local preparation of entanglement would be, instead of having two qubits doing a CNOT and doing the measurement, you would basically firstly prepare the qubits in some unentangled state and then do a CNOT gate, and then they would come out as entangled. And now that measurement is important because it can actually implement teleportation. So imagine that I already somehow had resource and was able to generate this long distance entanglement, like between this qubit and this qubit, and I was already able to generate an entanglement between this qubit and that qubit. Then it turns out that this Bell measurement that projects these two qubits in an entangled state, it simultaneously teleports the information that is in this qubit into that qubit on the right. And so that's why you could think that this is an operation that enables you to connect short distance entanglement to long distance entanglement. Because effectively what you can think is that the entanglement of the right is used as a resource to teleport this bottom qubit to the right here. But since that qubit was already entangled with this qubit, if the information from him is teleported to here, now we end up with this long distance entanglement here and the local short distance entanglement here.
Right. Okay. And I guess the problem of amplification still persists currently, but I guess we'll get to that in a second, because really what you have in the top figure is an equivalent scenario, more or less, if you don't have some form of amplification, I would say, to the bottom one, right? Or if I'm not missing something there. So the idea here is that so the naive way would be that you would try, in order to generate entanglement between Alice and Bob, you would try to send a photon all the way from Alice to Bob. And then you have this exponentially long fiber, and that means that the probability that this photon arrives decays exponentially with distance. But now, if you have this station in the middle and it has quantum memories, then you can beat this exponential scaling, because you don't need to simultaneously be able to transmit the photon from Alice to the middle and the middle to the right, because the memories in the middle give you some kind of what you may call like time independence. So the photon, let's say Alice tries to maybe Alice generates entanglement between her memory and the photon, and she tries to send the photon towards the middle station. And at the same time, maybe the middle station generates entanglement between that qubit and another photon that it tries to send to this station. And then at some point, maybe one of these entangled links succeed. Then that entangled link can be stored in a quantum memory, while the other one is being tried to be generated. So somehow the fact that you don't need to succeed both of them at the same time
you can basically overcome one half of this exponential, one half of the distance kind of in one round, and then maybe the other half in some other attempt, means that you can overcome this exponential scaling.
And when we're talking about the exponential scaling, are we talking about the likelihood of success of sending a photon that makes it across? Okay, then I think, then it's clear. So we split it up in two, and then we essentially get half, like you said, for, well, we circumvent half of it. Okay, thank you.
Right. So because the scaling is exponential, the transmissivity would be just the square root of the total distance. So you would say that the losses over half of the distance are basically the square root over the transmissivity. The probability of successfully transmitting the photon over half of the distance is the square root of over whole distance. And by splitting, and the idea is that by splitting this into these elementary links, you can basically overcome this exponential scale.
Right.
Also, actually, I have a slide for this here. So the crucial part are these memories that maybe I already succeeded in generating entanglement on the left, and then there is some qubit stored in this memory, and then I'm still attempting on the other side. And then this independence enables me to achieve that. So that is the kind of the method that was being developed over. That was kind of like the background of these quantum repeaters, how people were mostly looking at it from the beginning, where these quantum repeaters as a way of overcoming losses emerged at the end of 90s. And this is actually the strategies that we are trying to actually implement experimentally in various different physical platforms. But the strategies have certain limitations, is that each of those Bell measurements and these operations, there's kind of a lot of classical communication going on there, and these processes are actually not very fast, and also, as we mentioned, you need these quantum memories that are very long-lived. So there is kind of a new approach to that started to emerge, maybe let's say over the last 10 years, is to try to see whether you can use quantum error correction. So instead of generating this entanglement by just these short distance links that you connect, you try to do something like it is being done in a classical setting. So in a classical setting, we use some classical error correcting codes. So can we use quantum error correcting codes to overcome losses? So what you would do is you would say that you have some number of qubits that you encode a logical qubit, you send them through an optical fiber, and then provided that sufficiently many of those photons arrives, because the photons were together in a code word of some code, if sufficiently many arrive, you can still recover the information, correct it, like substitute the missing photons there, and then send it again over the next hop.
Is the reason for this to try and improve upon the transmissivity of the channel, or is it more to have more robustness against potential issues that might creep in during the course of sending it across? Like, because you could have redundancy in sending photons, right? So that you have more, let's say, attempts with the same information to try and transmit the information in a more likely way. I guess that's not what we're trying to do. I would guess rather what we're trying to do is to hedge ourselves against us sending a quantum state across this channel and then having some interference, let's say, or something that disturbs the quantum state when in the readout.
Well, when you refer to the single photons, do you refer to just like sending individual photons one after the other, or?
Yes. So I take it that these 6 yellow circles that we have in the figure now are a redundancy in the state. Like they all convey the same information that we're sending across. And the reason for putting in place a sort of quantum error correcting scheme like this to begin with, like just as far as the motivation goes for why we would deem quantum error correction a necessary part of this transmission, is that because in a setting where we would not have this redundancy, like let's say naively we would send one photon across one of these yellow circles, is the concern that upon receiving that the information would somehow have been affected during the propagation and that it would not be reliable, or what is it that we're trying to circumvent or address with the quantum error correction in this case?
Oh, it is exactly the same as here. So basically the only let's work in this kind of perfectionist model where the only problem that we have is the probability that photons can get lost in the optical fiber, and everything else is perfect.
Okay.
So basically one approach here, this original one, was to say that I'm trying to send these photons one after the other individually, exactly as you mentioned, but I can try to send them only over short distances, and I don't need to succeed kind of with, if you think that this process is happening in rounds. So let's say there is round number 1 and every repeater sends a photon to the next repeater. And then there is round number 2, round number 3. So the probability that all repeaters succeeds in transmitting the photon to the next repeater in the single round is effectively exactly the same as the probability that the sender sends a single photon in a single round all the way to the receiver. And that scales exponentially. Yeah. But here we were overcoming that by saying that they don't need all to succeed in the same round because the repeaters have memories, and then they can, some of those that already received the photon can store it while still waiting for the ones that didn't receive it. So that was the kind of the original approach. And the new approach is that this error correction approach is that we are still sending kind of things one after another, but in each transmission attempt, we encode our information. So let's say on this picture in 6 photons. And then let's say if one of those photons get lost, we can still recover the information from 5 remaining photons independently of which of the single photons got lost. And then if you do the calculation, basically you use the codes where, so in this example, that would be because transmitting any 5 out of 6 photons has a higher chance of happening than transmitting a single photon just in a single packet.
Okay, so maybe I think maybe I get it now. So we have one-way communication in this, and that not only applies for the quantum information that we're sending across the channel, but we also do not allow for, let's say, classical communication between the different quantum memories. Because you could imagine that we're splitting this segment now up into many different smaller pieces, like you have on the figure, and then we would just send one photon from stage 1 to stage 2, let's say. We, if the photon doesn't arrive there, there's no way for repeater 2 to, let's say, communicate with repeater 1 and know that it's still waiting for the information, let's say. Because that's how I envisioned it originally, but it seems like we don't have the ability to make that kind of back and forth communication between the repeaters in a classical sense to convey whether the quantum information has been sent or not.
Okay. Yes, so that's a very good point. So that's something that we are trying to overcome with this error correction. So in this architecture, it is assumed that in these ones where we generate the short distance links and connect, it is assumed that we have that capability. But the reason why we don't want to have that capability is that slow things down. So if every time I send something to the next repeater and the next repeater needs to communicate backwards whether it was successful or not, and then maybe that guy is resending again, then that procedure is very slow. So this new approach of using one-way communication with error correction is precisely the idea that you never need to communicate back, not because you cannot, but simply because you know that if you need to communicate back and the repeater 1 needs to do something adaptively based on that information, then the process would be much slower. So this architecture is supposed to be much faster than this one.
Okay, understood.
Yeah, and at the same time, so in order to make it exactly, so you want to make it much faster, and in order to make it much faster, you say, I don't want to use this backward communication. I want to kind of make a guarantee that instead of sending this single photon that with high chance is not going to arrive, and I will need to tell repeater 1, please resend. Instead of doing that, I can really just say repeater 1 encodes something in a code such that with very high probability, at least the number of photons needed to recover the information arrives, and then the repeater 2 near deterministically with probability close to 100% receives at least the number of photons needed to recover the information. It doesn't need to tell anything to repeater 1, can correct, meaning substitute the photons that got lost, and then send it again to the next one.
Okay, that's clear.
Yeah, is that okay? So I just wanted to kind of emphasize that there are these 2 approaches of how one implements quantum communication. Either using this remote entanglement generation where you have these segments, or using this error correction. And the one where you have this entanglement generation where you divide it into these segments where you generate these short distance links, and then you connect them using these Bell measurements. That's the one that is very time consuming, is more experimentally friendly, because for error correction, you need large number of qubits. But that one is slow and requires quantum memory, long-lived quantum memories. This one is more advanced because you need to be able to operate of large number of qubits, photons in the transmission, or maybe matter qubits in the repeaters. It's much faster, but you also don't need long-lived quantum memories because you never store anything for longer than just the time to locally perform some corrections and send it again.
Right.
So that is kind of the first kind of one novelty that started to be introduced around 10 years ago, is to use error correction also for quantum communication. And then the second one that we kind of introduced in communication in this paper is what kind of encoding we want to use for these qubits, what kind of error correcting. So in the standard encodings that for photons that have been generally used so far is either something that is called single rail or dual rail. So single rail just basically means that your 0 of the qubit is in the absence of a photon, and the presence of a photon is your 1. So that's something called single rail encoding. Or dual rail encoding is something where you think that you have two distinct modes, which you can visualize as two kind of separate maybe channels here. And then you have something either in one of them or in the other. So 0 would be something in one of them, 1 would be something in the other. And physically, that would correspond to, for example, polarization. So you say that you have a horizontal polarization mode and vertical polarization mode, and your photon lives either in the horizontal polarization mode or in the vertical polarization. Yeah, is that clear?
Mm-hmm. Yes. But let's say you had a superposition of these as well, or what are we trying to convey exactly with the encoding? So let's say you wanted to convey some form of state that's in a superposition of 0 and 1. How would that work in either of these? Because it seems like we're using a classical communication approach for encoding potentially quantum information, if we're looking to encode quantum information to begin with.
Exactly. Yeah. So you can have superposition of the two, and it's for dual rail encoding is much easier to implement the superposition because, for example, what would be a superposition of horizontally and vertically polarized? That would be some kind of a circularly polarized photon, or some kind of diagonally polarized photon. So basically, this is how you can achieve then this superposition, and then you can talk about these multiple bases and then the fact that this is actually a qubit. For the single rail encoding, that's a little bit more tricky because you need to have something where you have a superposition of presence and absence of a photon. But you can also achieve it in certain scenarios where you prepare something that is in superposition, the photon is there and is not.
Okay. Fair.
So these are kind of the standard ways of encoding qubits. And then what you can do is you could build some kind of error correcting codes on top of that encoding. But there is also another way to look at encoding qubits, which is basically this bosonic codes. So bosonic codes, here we talk a little bit about the quantum optics perspective, where basically we have this quadrature phase space. So the quadrature can correspond to position and momentum, or for electromagnetic fields, we talk about amplitude and phase of the electromagnetic field. And then, for example, what is represented here is a coherent state. This is the most, this basically a most classical state that can be generated with a laser. And then we see that we cannot have in quantum optics or in quantum theory in general, we cannot have a single point in that phase space because uncertainty principle tells us that we cannot simultaneously measure these two conjugate observables. So they cannot be simultaneously defined for any quantum state. And so the idea to use these bosonic codes for quantum communication, I mean, it kind of is also linked to classical. So in classical, we also use this. There is something called binary phase shift keying, where these are just now classical bits. We encode them in some two opposite states, like classical states, also in such a phase space. Or there's something called quadrature amplitude modulation, where we basically can transmit a whole bit string depending on where in this phase space we prepare our state. And so these approaches can also be used in quantum. And why do we want to use these approaches? Well, this is because it turns out that for this approach that I described here with individual qubits, it turns out that, so I mentioned to you that like, oh, we transmit 6 qubits, and then if one of them gets lost, we still get sufficiently many such that we can recover the information. So in practice, it cannot be 6. You need to have encodings where you have more than 100 qubits per logical qubit, which is quite challenging. But the pure loss channel, which we basically, the mathematical pure loss channel is a mathematical channel that models the optical fiber, basically a channel where things can disappear. It is actually a bosonic channel. So this is a channel that can be described in this continuous variable phase space. In fact, it admits states that live in this continuous variable phase space, and that phase space is infinite dimensional. We are not restricted to qubits. So we can make more efficient use, and instead of sending this large number of this single qubits, where each qubit is in this single rail or dual rail encoding, we can actually already transmit the these full bosonic modes. And in that continuous variable phase space, you can actually encode something more complicated that maybe tolerates losses better than just this combination of these polarization qubits. And then one example of that is this GKP code that I will soon introduce. And then we can think of this GKP code that you concatenate with some other code, meaning you can take multiple of those GKP qubits and then entangle them together to get some even more protection from loss.
Okay. So when we refer to GKP qubits in this case, are we referring to the entire packet that you now have displayed, or are we still referring to individual photons, let's say, within that, or individual peaks in that diagram?
No, so we are referring to the whole state. So there will be, I will describe that in soon. So we are referring to the whole, like, so if you think about in terms of this quadrature amplitude modulation, so you can think that you have a single state that is a superposition of all of these peaks that in classical you would have one of this, you basically, each of those peaks correspond to some different bit string. But now we can prefer some large complicated non-classical states where you basically have superposition of all of those different peaks. So this is a state that effectively is not a state that has a single photon. This is a state that has superposition of different photon numbers. So in this quantum optics picture, a mean photon number of the state is described by the distance away from the origin. But if your state is delocalized in the phase space, then that means that there is no fixed photon number. Actually, your state is a superposition of very different photon numbers.
Okay. The other point I would have on this slide is when we're saying that we need more than 100 qubits per logical qubit, is that more or less irrespective of the distance, or are we saying that with some particular distance in mind? How dependent is that number on how long the transmission? No.
Right. So I think that was roughly let's say for around 1,000 kilometers. If you want to communicate over, say, 1,000 kilometers, you need to place these quantum repeaters every around 1.5 kilometers, and then each of those repeaters every 1.5 kilometers needs to be able to process and correct errors on more than 100 qubits.
Okay, understood. Thanks for that.
Okay. Yes. So okay. So that's clear. Yeah. So here I said I also found that there are some other types of quantum repeaters that are much cheaper. That only costs 99 cents. So if the only other fails, we can move to use this one. Okay, so now I'll try to briefly introduce how this GKP code works. So as I said, you position and momentum. There we have this Heisenberg uncertainty principle that tells us that we cannot measure both of them simultaneously, but you can simultaneously measure them modulo some fixed quantity. So if you think about it, if you put position and momentum in the exponent of the operator, and now you say, I don't want to measure position, I want to measure this operator, SQ and this operator SP, because these are complex exponentials, right? They kind of they basically describe the phase on a circle. Then because of this periodic condition, effectively by measuring SQ, we are not really measuring exactly position. We are measuring position, in this case, modulo square root of pi. And if we would measure momentum, we will also measure momentum square root of pi. And it turns out that even though position and momentum do not commute, these two operators do commute.
Is there any form of intuition behind that? So we're saying they commute, and we can accept that from a mathematical point of view. Is there any way to think about why those two operators would commute, given the fact that, let's say, just the raw, let's say, quantities do not?
So you can think of it in terms of information, information gain. So somehow you cannot simultaneously define and gain information about both position and momentum. But if you are gaining just information modulo square root of pi, you are not gaining full info. Like you are gaining effectively less information, right? Because you only know that your state, you get only getting in this case you are getting an information between minus square root of, so in this specific example, minus square root of pi over 2 to plus square root of pi over 2, and you would be getting that independent. So for example, you will be getting an outcome 0 independently whether your actual value of position was 0, square root of pi, 2 square root of pi, 3 square root of pi. So somehow you are extracting less information. So now you can say that while you cannot extract full information about both of them, or rather a state that has that both types of information that are fully well defined does not exist, there exists a state that has defined position and momentum up to just this periodicity, and then that limited amount of, you can call it more limited amount of information, because just modulo square root of pi, that one you can extract simultaneously.
Okay. Are these two, so the operators at the top, SQ and SP, are they what we refer to as GKP states, or what are GKP states? Because I guess they're related to the code, right? But I'm not quite sure exactly what those are.
So GKP states is, so every quantum error correcting code is defined by some stabilizer operator. So you define some operators for qubits, for discrete variables. They are Pauli operators. And then a +1 space, any state that has an eigenvalue +1, where acted by this operator, would be a state that lives in the code space of a given code. So here it's exactly the same. So we can define a family, we can define a subspace such that if we act with these two operators, so they are called stabilizer operators, if we act with those operators on those states, we get an eigenvalue +1. And these are the states that I've written here. So for example, superposition of, so a logical 0 we define as a superposition of even multiples of square root of pi, and 1 as odd superposition of that. And then you see that if you apply an operator, you can show that if you apply an operator SQ and SP to both 0 and 1, you will get an eigenvalue +1. These are eigenstates of these two operators with eigenvalue +1.
Okay.
And so any state that is a superposition of the 0 and 1 will also, by linearity, also be a +1 eigenstate of these two operators. And so that kind of is our code space. And if you think now about this phase space, you can visualize this state by such a grid-like structure, right? So this is a superposition in Q, and it is actually, if you draw it in the other axis, like in P, it will also be a superposition. So if you look at this kind of Wigner function representation, which is this kind of quasi-probability distribution in both Q and P phase space, it looks at this kind of grid-like structure where you have these peaks that are basically periodically spaced. And then there are also some blue regions, which are the regions where the Wigner function, which is this quasi-probability distribution, goes negative. And so if the Wigner function goes negative, that means that the state is highly non-classical. And such non-classical state generally is quite difficult to prepare experimentally. So this is just to show that as you would kind of expect, if we use such a fancy resource, we would have require quite significant experimental capabilities to actually generate it.
Mm-hmm. Okay, and so the states that we represent, let's say, so you have the 0 and the 1 encoded variables down at the bottom. Are
Mhm.
they somehow represented now in the grid by the yellow by the red points in this case, or how do we connect, let's say, the grid-like structure in the top right corner with the functions that we saw at the bottom?
So basically, what okay, so there is the first caveat that I want to make is that these equations that you have in the bottom right corner, there are some kind of idealizations, because they assume that you have superposition of infinitely many peaks, and all of those peaks that happen at this either even or all multiples of square root of pi, that they are like Dirac delta peaks, and we have a superposition of infinitely many Dirac delta peaks. That's unphysical. It would require infinite amount of energy to prepare that state. So the state that you see in the top right corner, it actually, I mean, it doesn't have Dirac delta peaks. It has some kind of like Gaussian peaks that you see, they start fading as you move away from the origin, because they have finite energy. So there is this one approximation that I want to make. And now the second, how you would go from one picture to the other, is that the meaning of this Wigner function is such that if you take a marginal distribution, meaning you integrate across one of those two quadratures, you get exactly the distribution, you get the correct distribution along the other one. So in other words, these expressions here, the 0 and 1, express the state in terms of the Q quadrature basis. So that means that this is some description, a mathematical, or in this case, visual description of the state, such that if you write a mathematical function of this object that is here is both function of Q and P, if you integrate out P, meaning you take the marginal over P, you should be getting exactly this state along the Q axis that is described by these equations.
Okay, thanks.
So maybe so this is what I already mentioned, that we can simultaneously measure both Q and P modulo square root of pi. So here I think I have some slides that try to explain maybe how this error correction works. So indeed, I think it's much easier to think about it if we just look along just one axis. So let's say we just look at the Q axis. So you see here we have the 0, we have 1, and both 0 and 1 have peaks only at multiples of square root of pi, except that 0 has at even ones and 1 has at odd ones. And now, so you would see that if you measure Q modulo square root of pi, such that your outcome lies in this interval between minus square root of pi over 2 to plus square root of pi over 2, no matter whether the state is in 0 or whether it's 1 or whether it is any superposition of the two, we should get outcome 0, right? Because whether any odd or even integer multiple of square root of pi, if we take that value modulo square root of pi and shift it towards that interval, that would always give us 0, no matter where we are, whether we are in this peak, this peak, this peak, this peak, this peak, anywhere in that picture. So that tells you that such a measurement that measures Q modulo square root of pi, and that measurement is exactly this measurement of this operator as Q, does not reveal any information about the encoded state. It doesn't tell us whether the state is in 0 or 1. Yeah, is that clear?
Not exactly. Could you elaborate on that a little bit?
So basically, okay. So let's take some examples. So let's say if I collapse my state to 0, and then so basically let's start by saying that any outcome that I get can only be in the interval minus square root of pi over 2 to plus square root of pi over 2. So if I measure 0, that's already in this interval. If I measure 2 square root of pi over 2, this is outside this interval. Oh, I'm sorry, there is a typo. The square root should not go over 2. It should just go over square root of pi. So if you are in the peak that has a value 2 square root of pi, then since our outcomes can only be in this interval, we need to modulo this periodic.
When you're saying the measurement can only be in the interval minus square root of pi over 2 to square root of pi over 2, are you talking about a displacement from the 2 square root of pi point that we're looking at now, or how did those two values relate to the interval that we're looking at the top?
So that's saying that the measurement that does not reveal to you whether you are, so for example, the measurement will not reveal to you whether you are in 0, whether you are in square root of pi, whether you are in 2 square root of pi, whether you are 3 square root of pi. It will distinguish whether you are in 0 square root of pi, 2 square root of pi, 3 square root of pi, and whether you are maybe in like some epsilon plus square root of pi, epsilon plus 2 square root of pi, epsilon plus 3 square root of pi. So basically it will tell you, the measurement can tell you any shift from 0 up to minus square root of pi over 2 to plus square root of pi over 2. But if, for example, you had a shift from 0 all the way to square root of pi, that by this periodic boundary condition will be mapped again to 0.
Right. Yes.
So basically what I'm saying is that all of those numbers that you have on this axis here and here, if you bring them, if you keep subtracting from them, let's say you take 2 square root of pi and you keep subtracting square root of pi until you get to that interval, you will hit 0. If you take 7 square root of pi and you keep subtracting square root of pi until you are in this interval, you will hit 0.
Yes.
But now, so that was what I meant by saying that it doesn't reveal you what's the logical information. That if you measure this state and if you measure this state, that outcome will always be 0.
Okay. So what we're saying essentially, let me try to just repeat this to make sure I'm not, let's say, totally confused. We have these operators that give us some information that we can measure about the states. They don't give us full information, obviously, because then, well, we would break the uncertainty principle, but they give us partial information. And the way that manifests itself in these measurements is that we're able to measure, so long as the displacement from one of these points that you have in the top part of the graph is small, then we can tell essentially that, okay, this is the displacement. But the lens, let's say, that we're looking through is only a specific region. And so far as the displacement that we get is actually outside that region, we have no information as to whether or not it even, like, we have no information about the exact displacement then, because we lose the information of this modulus function over whatever the periodicity is, to square root of pi.
Exactly, yes.
Okay, cool.
So that's why the easiest way to think about it is, rather than thinking of where you are, or this is where the grid-like picture enters. So instead of thinking of where you are on this axis, it's easier to think that you have this kind of grid, and now this grid as a whole can shift, right? So here now, let's say that we have some noise that shifts all these grid peaks to the right, like drawn here by these dashed lines. So yes. Now, if you measure this q modulo square root of pi, now you will get some value that is non-zero, right? Because this, let's say this shift was epsilon to the right. So all the peaks, you originally had a superposition of those peaks at 0, 2 square root of pi, 4 square root of pi, 6 square root of pi, and so on. And then there was some noisy process that shifted all these peaks by epsilon to the right. So now we have a superposition of peaks at epsilon, like for the logical 0, it would be at epsilon, 2 square root of pi plus epsilon, 4 square root of pi plus epsilon, and so on. So then if you perform this measurement of this SQ operator, you will get epsilon.
Yes.
Yeah, is that clear?
Yes.
Right, okay. And then you would get that epsilon independently whether the state was 0 or 1. So that is nice, because that tells you that you are not revealing the information whether the state is 0 or 1, and yet you know that there was some process that shifted everything. And you know by how much.
How come it doesn't reveal the information whether or not it's 0 or 1? So we didn't really touch upon like how the 0 and 1 state in this case, so they live on the same axis now. And I think they did before as well, if we go back to the equations, because I guess the equations that we were showing on the previous slide are directly linked to the to the axis that we're displaying now. So they live on the same axis, and if we think of it as a grid where everything shifts, then fine, we're not able to distinguish whether we're in 0 or 1. But if we have a state that we encode, so I think my confusion is here. If we have a state that we try to encode using this kind of formalism, and then we have these equations to describe the state, do we then have peaks, let's say, both where the zeros and ones are? I guess if we're in a superposition of an encoded 0 and a 1, we would have peaks on both of them, but we're saying that we cannot distinguish between the 0 and 1. And I think that's where the confusion comes in a bit for me now.
Okay. So
we're somehow supposing that we have some state that has a non-zero probability for all of the peaks associated with these series, both of the series. And then if we take that to be the case, then a shift, definitely I agree, then we're not able to tell whether it's which one, well, whether it's 0 or 1. But I'm not sure if I'm thinking about the way we encode the information here in the right way.
Okay, so indeed, so of course you want to, like, there is a difference between 0 and 1. You can perform a measurement that that checks whether the state is in 0 and 1. So you can do a destructive measurement. You can just, so you can take, you can do a measurement that you don't measure SQ, you can do a measurement that just exactly measures the Q quadrature. Then by uncertainty principle, you destroy all the information about the P quadrature, but then you can find whether the value that you measured is an even multiple of square root of pi or odd multiple of square root of pi. If it's even, then it's 0. If it's if it's even, then you measured 0. If it's odd, then you measured 1.
Okay.
So this is how you can distinguish, right? So this is how you can distinguish. Sorry, is it clear?
And so we preempt the things that you said before by putting this through the lens of correcting errors that arise during the propagation, not so much trying to extract the information. Because I guess if you do that kind of measurement, then, well, you destroy the quantum state in doing so, and that's not what we're looking to do. We're just looking to correct it. Is that why we're saying then that we're not, that we're not distinguishing? Okay, gotcha. Thank you.
Yeah. So your error correction, you want to be able to do the measurement that just checks whether there was an error and what kind of error there was, without actually revealing the information that is encoded in the state, because you don't want to yet measure the qubit. You just want to correct the error, and you want to be able to do that without needing to. So you want to find out what the error is without finding out what the state is.
Right. Okay. Perfect.
And that's kind of what is kind of described here, that if everything shifts, you can basically figure out that there was a shift by epsilon without figuring out whether the state was 0 and 1.
Yeah.
Right. And then you can do exactly, and everything is analogous if you describe it on the other axis. So here, for example, now if we look at this and these two-dimensional picture. So let's say we idealize things now such that we have these black dots are where we have our Dirac delta peaks. And now, so we said that we can always measure things modulo square root of pi such that it needs to be within the square root of pi over 2 box. So let's say the central point that you had here, it shifts to, like, there is some noise process that shifts it to the location of the green square. So the whole grid kind of shifts like this. Then you would be able, by measuring this SQ and SP, you would be able to find such epsilon without destroying the state, and kind of then apply a displacement back by minus epsilon and then correct it. But of course, every code has this limitation. There is something called the distance of the code, which means that if the error has too high weight or the error is too large, then it is uncorrectable. And so what that means here is, like, let's say that this point from here, the noise shifting error was so large that it shifted this point all the way up to here. So now the shift was larger than this square root of pi over 2 kind of resolution of this box. So square root of pi along the q axis and square root of p over p momentum axis. So if the state shifts all the way like here, we will think that the actual correction that we need to apply is just, again, this short one. We would think that the state that happened to be here was actually coming from here, because that's the nearest kind of central location of within our resolution.
Yep.
And that means that effectively we ended up with this net shift that is illustrated here.
Mhm.
And such a net shift by square root of pi is a logical error.
Right.
So somehow you can argue that this code can correct small shifts if they happen within this resolution of this box. If the shift is too large along the momentum axis, we will get a Pauli Z error, Pauli X error if it's along the other axis, or a Pauli Y error if it's along.
What is it that limits the resolution of this box? Like, or well, rather the other way around. What is it that prevents us from making these squares infinitely large?
Right. So this is exactly the uncertainty principle. So you can think that uncertainty principle imposes a restriction on the area of this box, and you can kind of manipulate it such that you can make it, for example, rectangular. You can make it hexagonal, but the area is kind of fixed. So you cannot define a larger. Yeah, you basically you would find that you cannot find a state for which you could define this nice commuting operators if you wanted to have a much larger box.
Okay. Would there be a way to, let's say, contract it in one dimension? So let's say we would contract it in the x dimension, but then encode most of the information on the y-axis anyway. Like, because we had this, if we think about the two axes that we just played on the last graph, we had the encoding for the 0 state and the 1 state, and they were living on the same axis. What is it that prevents us from, let's say, shrinking this in the x dimension, pulling it out in the y dimension such that the error is preserved, but nevertheless we encode all the information in the y direction that we're anyway interested in? I guess we're violating something in that case, but I don't quite see what we would violate.
So you can make the box rectangular. So just to make okay, so one thing just to make clear, the information is not really encoded along the q axis. It's just that it's a little bit like the basis, right? Like for qubits, every state you can, or in just like in linear algebra, right? We can have multiple different bases, and you can represent a state in any basis. That's the definition of a basis. So here it's just saying that this state is represented here in the q basis, but you can, but there is a way of going through the q basis to the p basis. So you could also represent it using the p basis. So in fact, an eigenstate of q is the q and p are just Fourier transforms of each other. So you can transform these q's into p's, and then you will find that this logical 0 can also be expressed as a superposition of p states. So somehow I wouldn't say like, so the information is encoded in that space according to the spacing of these peaks, but I wouldn't say that the information is encoded along one axis.
Okay, I see. Would it then be, this is a super naive question, but would it then be possible that, like, let's say you would try to do what I described, you would contract it along one dimension and then extend it along the other? So you would then pay the price, I get, like, the state is not localized in one of them, and it would have some funny effect, I guess, on how distributed your state actually becomes in the two dimensions. Like, it's not that your state is sort of, that the uncertainty of your state is like a cloud and that you can manipulate these boundaries around it, but really they're inherently linked in some sense. You express it in one dimension or another, but you're not getting around the problem of, it seems like you cannot decouple the two. Yeah.
So you cannot decouple, but what you can do is you can modify so here the operators SQ and SP have both 2 square root of pi in the exponent. It's just that I think their product needs to be 4 pi by the uncertainty principle for them to commute. But you can also modify it. So somehow on this picture here is a general setting where you can have the spacing in one axis to be 2 alpha and in the other axis 2 pi over alpha. So you don't need this spacing to be the same. So you can stretch, you can kind of make these peaks further away along one axis, and then you would need to make them more narrower in the other. So basically what you would then get here in this picture is that you will get some kind of let me go, so this is covered. Okay, yeah. So then you would get some kind of rectangular boxes, right? They will be stretched in one direction. They would be wider, let's say, along the q axis, and they will be narrower in the p axis. So that is possible. Yeah.
You can do it. So that's perfectly clear. You can do it like that. The thing that I was trying to wrap my head around, which I didn't quite manage, is like, let's say you did that. It's kind of a different, like, you cannot do that without somehow, because you can express the state both along the q-axis or the p-axis. Let's say you twist the shape here. It's not just that you have that you're able to do a more accurate measurement in that case along the p-axis, because they must somehow inherently, through the uncertainty principle, be linked, right? Because if you're squeezing it together in the x-axis, which means that if you would imagine having some uncertainty regarding your value, you're essentially keeping less information by squeezing it together like that. Do you understand what I'm trying to get to? I know I'm not explaining it very well, but
you can trade it off. So you can say that you design a measurement which enables to extract more information along one axis and less information on the other. But the problem what you face then is that, so I think it's helpful to think about it in terms of think that any displacement that shifts your state anywhere within the central box can be corrected. So now if you're, so actually, the optimal, if you have a noise that is kind of fully uniform, so you have an equal probability of shift in any direction, then so actually the optimal one then, as far as I know, is the hexagonal one, because the hexagonal would be the one where the distance to the boundary is basically the most similar in every direction where you go. But if you had a noise process that is very highly biased, so let's say you have a noise process that very strongly, like with high probability, can shift you very far away along one axis, and then with very small probability can shift you not so far away in the other axis. If that was the noise that you are trying to use this encoding to protect yourself from, then it would be a good idea to stretch these boxes such that they are rectangular.
Okay, thanks for that explanation. That clarifies it a bit.
Right. So that's something that you can do. Yeah. It's just that the reason why we are staying here with the square is that you can show that a photon loss actually leads to something that is basically more uniform, that doesn't distinguish between Q and P, acts basically like a uniform distribution. Yeah. Okay, so I think we already have, sorry, so time-wise, how...
Sorry, we're overrunning a bit. So I know with some of the upcoming slides that you have, you've already made a talk about that. I can link that also in the description for the video that we're creating. So we don't need to go through, let's say, all the details that you have associated with it. I don't know if you need to jump for something else, but
no, I have time. I just thought that maybe now it's kind of I mean, this is kind of all these ideas that now I think we kind of described, and now I can put it together how we can do communication. Yeah.
Yes, let's do that.
Okay, so let me just go through. So I mean, this is basically all what we have kind of discussed. So let me now show how we can put it all together to. Okay, so this is now a picture how you can put it together in a communication setting. So you can basically say that you can show that the photon loss effect that happens during the transmission is effectively exactly something that your photon loss is exactly something that shifts that grid. And if the shift is smaller than square root of pi over 2, you can correct it. If it's larger than square root of pi over 2, then you cannot correct. So the whole idea here is that you can also have like extra protection by entangling some of those GKP modes together. So you can think that each of those yellow objects here is one of those kind of GKP modes that lives in that phase space. And now this ribbon means that we entangle multiple of them together to somehow have a higher level of encoding, higher level of protection. So what that means is that if you try to do correction on the individual GKP qubit, and then you think that you have corrected an error, but in fact you didn't, because how I described there, your shift was larger than the square root of pi over 2. Your actual noise took you out of the grid, and then you basically, we ended up with some logical error. that logical error can be captured by a higher level code. So now if we entangle multiple of such GKP modes together, we can try to, instead of measuring just Q and P of each of those individual modes, we can try to measure some global property of multiple of such modes. And then, for example, there should be a global property that if we measure some Pauli operator, so a tensor product of some Pauli operators of multiple of these modes, you should be getting +1. But if on one of those GKP qubits we failed to correct an error, then now if we would measure that this global property of multiple GKP modes, we would get -1. So that would tell us that, on actually one of those qubits when we were looking at this Q and P quadrature of that individual mode, we actually might have made a mistake, and then we can kind of correct it on the higher level. So this is this idea why in the paper we talk about concatenated coding.
Okay.
Is that idea kind of clear on
Yes.
high level?
When it comes to this from a practical perspective, how far into the future would you say it would be for us, like putting all other, let's say, implementation constraints aside for a moment, just entangling these kind of states and being able to do that in a stable way? Is that something that's feasible? That's, let's say, on the margin of being feasible, or is it very far into the future in terms of what we're able to do?
So I think that depends. So I think it's difficult to say because we are trying to realize, like the community is trying to realize this state in multiple different platforms. So recently there was a first experiment where a single very proof of principle quality GKP qubit in like optics was realized, like purely optical. So that's something that we want for communication. Before there were much higher quality GKP qubits done in microwave cavities, but at microwave this is not the frequency at which we would want to do communication, because then of all this thermal noise, it would be very inefficient. But so far, no one has demonstrated multiple GKP modes that we can, as far as I know, no one has demonstrated multiple GKP modes that we can actually already entangle and interact and do gates between. So, but I think in this microwave regime, in this microwave cavities, I think that is something that within, I think, few years from now, we would be able to entangle GKP modes together.
Okay, cool. But the concept anyway is clear.
Okay. And so now the nice idea is that if you have such two levels of codings, you can also have two types of stations. So we said that we have this so-called quantum repeaters that correct errors. And so this is this kind of one-way architecture. And so we see that we can have these blue repeaters that only correct these errors on the lower level. So that they measure this SQ and SP. And then we have, and they only need to be able to store one of such GKP modes. And then we have some higher level code that entangles, let's say, maybe 3 GKP modes together. And then from time to time, we have this more powerful repeaters that waits until it receives 3 of such GKP modes. And then, like as marked here in this red one, if there was a GKP mode on which the blue repeater failed to correct an error, then we would still be able to detect it and correct on the higher level in this more powerful but also more expensive green repeater. So that's basically the setup, and here are maybe I'll show some results, what we think, what kind of distances you would be able to communicate to. So basically only GKP means that you don't do this higher level concatenation. 412 code means that you entangle 4 GKP modes together to basically have a higher level code that consists of 4 GKP modes entangled together. And this if you encode 7 GKP modes together. And in the table, we consider some experimental parameters. So this GKP squeezing is somehow how close to this Dirac delta functions you can be with those peaks of that state. So the larger the squeezing in dB, the closer we are to this ideal state. And then coupling efficiency is some kind of like parameter we assume apart from losses in the fiber, how much extra photon loss you would have inside the quantum repeater. And the number in the table tells you like what kind of distance in kilometer we expect to achieve with these parameters. And the red regions are the bad regions, the green regions are the best regions. And so we,
Right.
not surprisingly, we see that the higher concatenation we do, the larger the grid region.
Mm-hmm. The squeezing here, is that, let's say a descriptor of quality in our procedure, or is it something else? Like, we're saying it represents how close our states are to direct deltas.
Mm-hmm.
The extent to which they are close to a direct delta function, is that, let's say, the result of how good does that contain the information of how well we've sort of done in the encoding when we use the information, or is that something that's more intrinsically physically linked, let's say, to the uncertainty principle or something like that? It seems like it's sort of a quality parameter of our system.
Yeah. So this is a quality parameter of the hardware. So you can also think that the more squeezing in dB, the more energy you need to put in the system. So like infinite amount of squeezing is infeasible, but we can go to, but we hope to get to higher and higher squeezing. So I think these papers in this, so basically, if you go into, sorry, so let me maybe go back. It's much easier to describe on the picture. Right, so if I look here, you can think, so we had this kind of Wigner function representation, and we said that we have this kind of peaks that actually are not Dirac delta peaks, they have some kind of width. So infinite squeezing would be that each of those peaks is super narrow, but those peaks continue up to infinity. And then finite squeezing means that these peaks are not super narrow, and they start kind of fading away as we move away from infinity. So fading away meaning that their probability amplitude is much smaller than those peaks that are located centrally. So you can think there is some kind of like a Gaussian envelope that goes over the whole object. And the larger we can do this Gaussian envelope, and the more narrower we can do the individual peaks, the higher the quality of our individual state.
Okay. And that's somehow is that an energy constraint, how big we can make it, or is it something else?
So I think there are so I think indeed there are a lot of factors here that are very intertwined. So it is an energy issue, but it's an intertwined issue that you want to be able to pump energy into your system in such a way that you can, like in very special way, right? You need to have this very special way where you're pumping the energy by actually forming this grid states. So energy here is a very broad term saying that you can increase the mean photon number in your state, but you want to be able to increase this mean photon number in this very special way that preserve this kind of grid-like structure. So doing this together is the difficult part. And I think if I just quickly add that experimentally these microwave cavity GKP qubits I think are on the level of between 7 to 9 dB. So you see that this is still much further into the future.
Okay, good. Thank you. I won't jump in with follow-up questions because I know I'm holding you for too much over time.
Okay.
But that's clear. Thanks.
Okay, so I think so I think I can basically close to finish here. I mean, what I wanted to say is that now the nice thing is on a high level is that, if you have these different types of concatenation, you can have this GKP repeater only. You can have repeaters that work with this higher level 4-qubit code and this higher level 7-qubit code. You can kind of design some kind of cost function, and you say, oh, I want high performance. So for example, I want high secret key per such an optical mode, but I also want to minimize the cost. And I can say that, oh, using this GKP repeaters is going to be very cheap, while using these repeaters that has that can operate on 7 GKP modes at once and entangle them together is expensive. And then I can, define some cost function and try to optimize it. And so can I just stop here, or if you want, I can show just basically like one because I have a plot that shows like, in terms of these costs, for example, or I don't know whether you want to go to some numerical values or.
I mean, if you have one and it doesn't take too long for you, then I'm happy to have a look at it.
Okay, so let me. Right, so basically the goal is to minimize this cost function, and so here is something that where we show basically this is our kind of arbitrary defined cost function that is basically the cost of those repeaters. We have some way of calculating what would be the cost of each of those repeaters depending on kind of for how long you need to be able to store those GKP qubits in these repeaters to do all the necessary operations in each of them. And then what we plot here is, as a function of distance that we want to achieve, what is the value of this cost function? And then we have 4 scenarios. So we have our scenario where we want to concatenate GKP. In our scheme, we concatenate GKP qubits with the 412 code. We concatenate GKP qubits with the 713 code. So 412 code is basically the one where we entangle 4 GKP qubits. 713 is when we entangle 7 GKP qubits. And then we also, for each of those, we have either a version with hybrid. So hybrid means, let's say hybrid for 412 means that we are allowed to use both these repeaters and the GKP repeaters. Hybrid for 713 means that we are allowed to use both these repeaters and GKP repeaters. And only type A repeaters means that we are only allowed to use these more powerful ones. So only type A for 412 means that we are only allowed to use these ones. Only type A for 713, we are allowed to use only these ones, but we cannot use these cheap ones. So in terms of performance, of course, we expect that the only type A would perform better, because if we can afford, it's always better to put the more powerful one than the less powerful one. But if we also have this cost in account, it turns out that the situation becomes a little bit more interesting. So we see that the hybrid lines, the blue line and the yellow line, is always below the corresponding only type A. So for the 412 code, the blue is below the red, and for 713, the yellow one is below the purple, which means that it's always, from the cost perspective, it's always better to use the architecture where some repeaters are the cheap ones and some of them are the expensive ones, because that gives us a little bit more variability. And then the second thing that we see is that if you want to go up to around, I think, a little bit more than 2,000 kilometers, the cheapest strategy is just to use this hybrid scheme with the 412 code. And then at some point, if you want to go to larger distances, this 412 concatenation is becoming too weak, meaning the blue curve starts overlapping with the red curve and they shoot up very fast, which means that if you wanted to still work only with schemes that uses these 4-qubit repeaters, you would need to place them very, very, very densely, and that's why it shoots off so far. But so then it's better to switch to these more powerful repeaters where you actually also concatenate with the 713 code. That's the yellow.
So we're using in the paper 4 and 7 as a number of let's say repeaters, or the number of entangled states in one of these more powerful repeaters. Are we constrained to some specific numbers, or could we make that anything we want? Could we make one with, let's say, 5 entangled states, or do we have some form of restriction there?
No, so we could use larger codes. So the reason why we considered 4 and 7 is that these are the smallest actually error correcting codes. So for qubit, like the smallest codes that we think would be we can use for correcting errors are okay. So there are a little bit of subtleties here, because 4-qubit code, if you're just using with discrete variable qubits, can only detect errors. If you concatenate it with GKP, it can actually correct errors. So the reason why we are using 4 is that's the smallest code that can actually do something useful. And 7, there is also a 5-qubit code, but the 5-qubit code is a little bit more tricky to describe mathematically. And then the next one is the 7-qubit code, which is the next one in line. But then there is another, if I would to go on, I could consider a 9-qubit code and so on. But our point here is that you don't need to go to larger codes. You see, even if you want to communicate between 1,000 to 10,000 kilometers, using just 4 or 7 is sufficiently enough. And so now if we go to this discrete variable, this polarization encoded repeaters, where I said that if you want to go to 1,000 kilometers, you need to entangle more than 100 photons. So now you have these different technologies. You can say either you need to be able to prepare 100 single photons, or actually more than 100 single photons that you can entangle together. Or you say, I only need 4 or 7 optical modes, so much less than this polarization, because remember from the dual rail encoding, every qubit in the dual rail encoded scenario occupies two modes, like say horizontal and vertical polarization mode. So more than 100 qubits would actually mean more than 200 modes. Here you only need 4 modes or 7 modes. So like the number of modes, that optical modes that you need is much less. But inside every mode, instead of just preparing a single photon, you need to be able to prepare this very complicated GKP qubit. So it's like a very different type of resource.
In terms of complexity of generating that state, is that something we're able to do at the moment, or is it far-fetched?
Right. So this is something that we had. So as I mentioned, in this microwave cavities, we already have this GKP qubits that are, I think, up to around 9 degrees of squeezing. Optically, some simple one was also recently realized, and then was also some experiments where they realized them in kind of not in light, but in phonon, so in vibrational modes of trapped ions. So single individual GKP qubits we already have. We don't have yet them in the high quality ones in the optical regime that we could really use for communication. But since the research in the GKP qubit is now very highly motivated also in the context of computing, I think that, and given the recent experiments where the proof of principle optical GKP qubit was generated, I think that yes, it might take a while, but it is definitely a promising alternative to trying to generate entanglement between more than 100 individual photons. It's just I would say an interesting alternative strategy.
Okay, perfect. Last question I would have from my side is just in terms of the research that you're doing now. I think you mentioned in the beginning that you have another paper that's building on top of this, and just in general, like what you're trying to do going forward with the results here. Is there any direction that you think is worth pursuing further when it comes to this research, or what are sort of the next steps?
So I think that there are kind of two directions. One is more theory-oriented, the other was more experiment-oriented. So the theory-oriented one, so when I say going from here, I say going from this high-level approach where, we design these architectures that we talk about communication over 1,000 or 10,000 kilometers. Because, of course, there can be also a bottom-up approach, right? The bottom-up approach would be someone gives me this specific hardware, and can I design a proof of principle GKP qubit experiment, GKP qubit communication experiment on that specific hardware? So that would be kind of a different framework. But starting from this approach that I presented here, so one direction would be how can you use these GKP error correction properties to design to obtain some more useful information. So, for example, you can find that this GKP syndrome, like when you measure this operator SQ and SP, I said that if the value is larger than epsilon, if the epsilon that shifts is larger than square root of pi over 2, then you would have an error, and that here we try to catch on the higher level. But what is the interesting is that you actually get some extra information. So if you measure that syndrome, if you measure it very close, if the number that you get, this epsilon, is very close to this decision boundary of minus square root of pi over 2 to plus square root of pi over 2, you know that it's it's much more uncertain because it's very close to this boundary. So it might be that it has come from the other side of the boundary, just jumped over. Well, if you measure something that is close to 0, you can probably think that it's much more likely that you have corrected your error well. So somehow this syndromes gives you some likelihood information about, in this specific instance, on this specific qubit, and in this specific error correction round, how reliable is my error correction procedure? And it turns out that information you can use in many different ways. You can think, for example, if you have some routing scenarios, you can say, oh, if this qubits, I collected a lot of high reliability information for these specific ones, maybe I can send them from one path. But if I got qubits for which I found this reliability information is not so good, maybe I will send them through another path, or I will use it for different tasks, maybe for some communication tasks that requires worse quality qubits, and qubits for which this reliability information is better, I would use for some other tasks that requires higher quality qubits. So we think that there is a lot of things you can extract out of these, what the specific information you get by measuring this SQ and SP operators. So that is where we are moving from this more, let's say, theory-motivated aspect. The experiment-motivated aspect here is like trying to design procedures where we can lower these numbers, basically. So how can we modify these schemes where we especially want to show that we can still communicate over reasonable distances, and we can lower this requirement of this GKP squeezing, such that it doesn't need to be of the order of this 15 dB, but go down to closer where we are now experimenting.
Okay, just one follow-up question on the noise that we mentioned before, and sort of the perturbation and how certain you are that the quality of your qubit is actually high. It sort of presupposes that the noise is always Gaussian. Is that always a fair assumption for these kind of systems? What kind of noise do we actually experience when we have perturbations in these systems? Is it always like some small deviation from the starting point, or could you have something like where it's much more a discrete kind of thing that shifts your structure quite a bit? Because I guess that that plays a big role in what we can say about the confidence, right?
Right. So so the reason why I guess there are two reasons why the Gaussian one is, I think, something that seems the most interesting one. So the first one is that indeed that's something that we would expect in the realistic scenario of photon loss. So if you actually had, let's say you send any quantum, this continuous variable bosonic states through an optical fiber, through a photon loss. So let's say you take a coherent state that is represented here as this kind of blob. You send it through a photon loss channel. So this photon loss would shrink this blob. It would move closer to the origin, right? Moving closer to the origin means that the mean photon number is the state is becoming produced. But then what you can do is you can apply amplification by you can do characterization of your channel. So you know that the transmissivity of your channel between A and B is, let's say, 90% or something, 60, 70 or 80%. So then you can do amplification, where you amplify your state by the amount that is given by the inverse of that loss. And what happens is that then the net shift is zero. So you started from here. It firstly shrunk towards the origin. Now you amplify it, so it goes back to where it was before. But I said that quantum theory does not allow noiseless amplification. The no cloning theorem tells us that we cannot put these amplifiers. So this amplifier will add noise. And this noise that comes from loss and followed by amplification, where the mean kind of stays constant, is actually a Gaussian noise. Okay, so that's the motivation why we work with Gaussian noise. And then the second motivation, of course, is the Gaussian noise is the easier one to deal with. So that's why when I talked about this reliability, what basically you can think is that you can imagine that you have these peaks, and then there is some Gaussian noise that shifts these peaks. And indeed, if you measure, and you can measure your shift only in this interval between minus square root of pi over 2 to plus square root of pi over 2. And then if you measure your shift you measure your value to be very close to this, to zero, then you know that, well, the actual shift could have been to here, or to here. But because you know that your noise is coming from the Gaussian distribution, the fact that the shift was all the way to here is much more likely. So then you say that by assuming that the shift was epsilon, you, with very high probability, correct it. But if you measure a syndrome very close to this boundary here, now this is consistent with these three arrows. And so now you see that the relative height of this arrow with this arrow is much more comparable. So now you are less likely. So you see, if you measure the syndrome close to the decision boundary, you are more uncertain about your actual error identification.
Yes, absolutely agree for a Gaussian. And it's clear now also that, well, with the amplification, you would expect to get a Gaussian noise. Thanks for that.
Right. Yeah. So I think to conclude, I guess what I already said is that I think that using these bosonic codes for communication offers an interesting alternative to this discrete variable codes, and I think that this is another very exciting research direction, simply because we already have the first proof of principle optical GKP qubits, and this GKP research field is also developing very strongly in the context of quantum computing. So kind of here the goals quite strongly align. I think the big kind of obstacle now and challenge is to be able to design this high quality optical GKP states, or if we are generating them in the microwave regime using this superconducting qubits that has already been done experimentally. There is a lot of research in experimentally developing a transduction, which is some procedure that would enable me to transform a state that lives in a microwave mode into an optical mode, with hopefully not adding too much noise or loss in this process.
Yeah. Awesome. Thank you very much, Filip, for taking the time and also for running over time with the interview. I really enjoyed the discussion, so thank you very much for it.